Hello, my name is Anthony Antonio. Today I'm going to be teaching you about Lewis structures. Lewis structures are simply made to show how molecules share electrons. So what I mean when I say that is, let's say you have water. So let's say we have H2O, and you want to show how they go together and how they're bonded. You would have to draw out the Lewis structure. Since we already have this, I'm going to go ahead and erase it. So the Lewis structure here, it's pretty simple. The first thing you do when you're trying to draw a Lewis structure is you have to figure out the valence electrons. The valence electrons are very important because they are what connect all the elements together. So here we have H2O, which means we have 2 hydrogens and 1 oxygen. So the way you figure out how many electrons you have is you have 6 oxygens because it's in row 6A, and you have 2 hydrogens, so that's 1 each because they're in row 1A. So you take 1. You multiply this by 2 because of how many hydrogens we have, and you add it with the 6 from the oxygen. So 1 times 2 is obviously 2, and 2 plus 6 is going to be 8. So now you have 8 to work with. The thing with, I have to re-switch the paper then. The thing with Lewis structures is you have to know which one you're going to make the central atom. In most cases, the central atom is the one with the lowest electronegativity. So right now it would actually be hydrogen, which is 2.1 over the 3.5 oxygen. However, hydrogen is void to that rule. So here, we're just going to go ahead and make oxygen our main atom. Now I'm going to go ahead and start us off and make the bonds. So this is pretty simple. How do you start it off? Now we have to try to figure out the octet rule. The octet rule just says that we have to have 8 valence electrons around every element. However, there is one exception, and of course that exception is hydrogen. Hydrogen seems to be wants to be the special one all the time. So now we have to figure out how to make this 8, but there's no more single bonds to attach it to. So now we have to go ahead and make these things called lone pairs. Lone pairs are these dots, and each of them represent 2. So we have 2 and 2. I don't know if I mentioned this earlier, but the single bonds here that I wrote down also represent 2 valence electrons. So now the oxygen has 2, 4, 6, 8. So we have 8, you subtract 8, and you have 0 valence electrons left, which means you did it correctly. The next thing I want to show you guys is our handy dandy chart here. I have written down formula, electron group, electron geometry, bonding regions, lone pairs of molecular geometry, are there polar molecular bonds, and is the bond or is the molecule polar? So I'm going to start this off, go by one with you. So we have water, which is H2O. Write that in the first one. The electron group is how many is touching the central atom, element. So we have 1, 2, 3, 4 touching it. And because there are 4 touching it right now, the next thing we have to do is we have to name this geometry. Now, since there's 4 usually is represented by tetra in anything chemistry. So I'm going to go ahead and call this tetrahedral. And since there are 4 bonds or groups touching the central element, that's what it's called. Now we go to bonding regions. Bonding regions is practically the same thing as electron group. You look at these, and there's 4. So that remains the same. Now we go to lone pairs. As I said earlier, the lone pairs are these dots. So now we have 2 lone pairs. 1, 2. So there's 2. Because of this, it's no longer going to be tetrahedral. It's going to change into something else. Now I'm going to show you what that something else is. Now this is how the molecular geometry goes. You have to draw it to where you can tell, like if there's an angle. So right here it should be like 180 degree angle. So the molecular geometry is now bent, and you can tell because the bonds are going opposite like that. So we have bent. Now we have to see if the molecular, or if the are there any polar bonds here? So the way you do that is I have this chart, and you can tell because if it's 0 to 0.4, it's nonpolar. Here highlighted in pink, courtesy of Kimberly, it is 0.41 to 1.8 means it is polar. And then if it's higher than 1.8, it's going to be ionic. So we come back over here and we check. Hydrogen is 2.1, oxygen is 3.5. That makes there's a 1.4 difference. So there is going to be molecular bonds. So yes, there are molecular bonds. Next up are the bonds polar. So what you do, alright, so I realized that I made a mistake in my first go through, and this is actually 109 degrees, not 180. So back to where we were with the molecular bonds. Yes, this is molecular bond because, or I'm sorry, there are polar bonds because the difference is 1.4. Now we have to figure out whether or not it's going to be a polar, if the molecule is polar or not. So how you do that is you draw arrows pointing towards the one with the highest electronegativity. And these are both going up. So because of this, H2O water is going to be polar. So yes, H2O is polar. Now to move on to something new to teach you guys, I have another formula in which it's a difference in the geometry. So I would like to show you guys the differences in the geometry now. Okay. So the next one I have written down to explain to you guys is carbon dioxide, which is CO2. Alright, so the same rules and principles apply. You have to come over here and you have to check your chart. You have to see which one has the lower electronegativity to see which one's going to be in the middle. We have carbon, which is 2.5. We have oxygen, which is 3.5. Carbon obviously is going to be the lower of the two. So it's going to be carbon in the middle with 2 oxygens. Now we already know we have to go through the whole valence electrons thing. So to figure out how many we have or how many we're going to need, we're going to figure out the valence electrons. So carbon is in row 4A and there's 1. And then oxygen is row 6 and there's 2. So we're going to multiply oxygen by 2, which is going to be 12. Add the 4, it's 16. So now we have 16 valence electrons that need to be used for carbon dioxide. Now carbon dioxide, let's see. So I'm doing this with you guys to explain to you how to do it. So carbon, you already have 4 gons, so 16 minus 4 is 12. I'm going to put double bonds. Double bonds are the same thing as single bonds. They only take up 2, but when they're double, they take up obviously 2, 4, 2, 4, so there's 8 now. So now we have 8, so I subtract another 4. You only have 8 left altogether for valence electrons. So now I'm just going to add 2 lone pairs to each of my oxygens, and that should be 8. You always go double check your work. So for the left oxygen here, we have 2, 4, 6, 8. He follows the octet rule. Our carbon has 2, 4, 6, 8. It follows my octet rule. The right oxygen has 2, 4, 6, 8. Also follows the octet rule. Now we have to go back up here and fill out the chart to see what we're doing. Okay, so the formula was CO2. The electron groups are 2. The electronegativity, since there's only 2 touching it, it's going to be linear. Bonding regions, there are 2, so that stays the same. Lone pair, there are 0. So that means, since there's 0 lone pairs, and it's the exact same in both of these, it's going to stick to linear as its molecular geometry. Now we have to figure out if there's polar bonds. So we come back to my helpful little chart over here. Carbon has 2.5, oxygen has 8.5. Difference is 1, so they are going to be polar bonds. This time, both of them are pointing towards oxygen, and since they're pointing away from each other, even though there are bonds, polar bonds in the molecule itself is not going to be polar. Oops, I meant to write no, but I started writing yes. So that is CO2, carbon dioxide. Now I have another one to show you guys. 5 of my viewers on YouTube. Alright, next up I have ammonia, which is NH3. Alright, as I said before, sorry about that. So as I was saying, we're now at NH3. NH3 is called ammonia, as I'm sure we're all aware of. So we have to, knowing the rules, hydrogen cannot be my central atom, so I'm just going to go with nitrogen. So we have nitrogen now, and we have to go ahead and figure this out. Because it's, well, I'll explain that later. So we have H, H, and H. So now we go back over here, we find to figure out our valence. We already know that hydrogen's in row 1 due to our earlier friend, and now we know nitrogen is row 5. So we have 3 hydrogens, so that's 3 times 1, which is 3, and then we add 5, and we have 8. So looking at this, we see that nitrogen is the only one that needs to follow the octet rule. The only thing we can do is add little lone pairs up top to put it down. Now, there's a special way to draw this type of molecule. Let me tell you what it is first. NH3, the electron group is 4. The electron geometry is tetrahedral, which I've already gone over earlier with H2O. The bonding regions are 4. However, there is 1 lone pair. So the molecular geometry is different. So let me draw this out for you. So this is what it's going to look like now that we've changed. This is supposed to represent 3D that is sticking out to you, and this is also supposed to represent that is sticking away. So now that we have ammonium drawn out like this, we can figure this out. This is going to be trigonal, and if you look at it from above, it kind of looks like a pyramid, so we call it trigonal pyramidal. So that's trigonal pyramid. Now we have to figure out the bondings, and if it's polar or not. Nitrogen has 3, hydrogen has 2.1, so it's a 0.9 difference. So it will have polar bonds. All of them are going to be sticking towards nitrogen. One of them do cancel out and the other one does not. So we're going to have the polar bond going up by itself. So yes, we have molecular bonds, and yes, the molecule is polar. So now that I've shown you those, I believe there's only 1 or 2 more that I have to show you before we are done with our fun little presentation. Okay, so I've done this one. Alright, so the last one, it appears, is CO2. I already did that one. Which one am I missing? Can you pause for a second? Alright, so sorry about that. The last one I'm going to show you guys is methane. Methane is CH4. As we already know, due to the earlier Lewis structures, hydrogen can never be in the middle, so we're going to start off with carbon being our middle guy. So obviously we need to draw 4 because there are 4 hydrogens. So we come back to our nifty periodic table of the elements. We find out the carbon is in row 4A. So there's 1 carbon, which is 4. There are 4 hydrogens, which is 4. So 4 plus 4 is 8. And now that we have 8, we're already done. So we look at this. 1, 2, 3, 4. Carbon is already following the octet rule. So it is CH4. Electron groups are 4. The electrogeometry is tetrahedral, as I said earlier, when we had 4 bonds touching it. The bonding regions are 4. There are 0 lone pairs. Molecular geometry, it is drawn a little different than this, so I'm going to draw it the correct way real quick. It was kind of like pyramidal. Oops, it's not that close. So that's the correct way to draw the molecular geometry for tetrahedral when you have 4 like that. So now we just need to figure out if the molecular is a bond or not, or if there's a polar bonds or not. Carbon is 2.5 and hydrogen is 2.3. So that's a 0.3 difference. So no to both of them. Neither is polar. Neither of them are polar. So that is it for my presentation today. I thank you very much for watching. I hope you enjoyed.